start recording here. So I think we're recording now, so take it away, Max.
So, as we all know, functional programming is really awesome. And according to the comic, XKCD, tail recursion is its own reward. But what is tail recursion? I was really confused by that for a really long time. I did some research on it, and as far as I can tell, there are 3 conditions that you need to have tail recursion. First is a tail call. The second is a linear iterative process. And the third is an interpreter that can run a linear iterative process executed using recursion that does not use the call stack. So why do we care? Well, it leads to a process that evolves in constant space. So what's a tail call? Wikipedia tells me that it's a subroutine call performed as the final action of a procedure. And as far as I can tell, I've underlined one here. But this implementation of factorial in Scheme is not tail recursive, because it generates a linear recursive process, not a linear iterative process. So the way that I think about this, and Hal and Jerry talk about, it's useful to imagine the shape that a procedure generates, like the shape of the process that a procedure generates. And in this case, this procedure generates a shape like this, that comes out like this, a linear recursive shape. And the important part of this is that the procedure doesn't evaluate until it hits the stopping condition of factorial equaling 1. And so it has to store all those computations in memory prior to that happening. It's not a big deal if you have like factorial of 6, but if you have factorial of like 700 million, then like you're probably going to get a stack overflow. So that's no good. Tail recursion requires a linear iterative process. This is another implementation of factorial that generates that kind of a process. And if we look at the shape of it, you can see that it doesn't go out like this, and it doesn't require storing variables in memory as the procedure executes. So it executes in constant space. So we can see the contrast here. The procedure on the left is tail recursive, and the procedure on the right is not. And so it uses the call stack in its execution. Hal and Jerry also talk about the registers. Like a register machine is a good model for understanding how a computer works. And so in their description, linear iterative process that is run on an interpreter that can do this kind of process and run tail recursion only uses the registers and doesn't have to throw variables on the call stack. Not all interpreters are capable of doing this. I know that Scheme is capable of it. I believe that Scala is capable of it. I know that actually Clojure is not capable of it. It has to use a special syntax called recur to make this kind of process happen. And all imperative languages are using for loops in order to generate a linear iterative process. So they don't have this ability. What was most helpful for me in trying to understand what tail recursion was is kind of being able to see the contrast between an imperative programming style and a functional programming style. The procedure on the top is factorial implemented in an imperative style, and if you can see on these arrows here that it uses assignment, and it's updating it at every iteration of the loop, which can lead to subtle bugs, and also it because it's mutating the data and updating assignment, it can lead to issues if you have like concurrency or things like that happening. Like for example, a bug, if you switch these two lines, you'll get the wrong result because you're updating the counter prior to doing this multiplication of the counter times the product. And this is not possible or is harder to have happen if you're writing in a functional style. The thing that like most struck me about this is, and like I was glad to kind of do some more research on this, is because the contrast is in that a functional programming style, you're not mutating data. What you are doing is updating the argument's values each time that you're calling the function recursively. So you can have immutability in your data because you're never going to change it. What you're doing is just changing, updating the arguments, and that really opened kind of a door for me in trying to understand more about how immutability is possible in a functional programming style. So that's tail recursion, and that's why I let you talk. Do you have any questions? Maybe I can answer them.
Well, like a discussion type thing. I was going over some free monad stuff, which might not be terribly important right now, but in that documentation somewhere, I said something about using like Yoneda or having a sort of embedding to get trampolines so you can do functional stuff with this. I don't know if anyone has any idea what I'm talking about.
I can speak to the trampoline part. I can't speak to the Yoneda stuff.
Okay.
So the trampoline thing is one way you can sort of get around the language not being able to kind of optimize tail recursion natively. And so the idea is that you've got a trampoline function which returns a function itself, and that as long as it keeps returning functions, you keep calling the functions that it returns, and that's sort of the trampolining of it. And when it stops returning a function, when it returns something else, so I guess technically it's returning a variant, like an either of a function or a result.
Right.
Once it returns the result, then the recursion is done. But as long as it keeps returning functions, you keep calling those functions over and over. And that way you can use, basically each function is returning, so it's deallocating its stack frame, and then you can allocate a new stack frame, but in that shape that Max presented,
right,
it never gets larger than a single stack frame at any given time. Well, I guess 2 stack frames, but it's...
It builds like small steps of computation, like one after the other.
Okay.
And in languages like Scala and Scala Z, like trampoline is basically implemented in free.
Right.
So basically trampoline is a type alias to a free, where in that free monad that S is your function. If you know what free is.
Yeah.
So basically, in any like Scala FP implementation I've seen, all free implementation are tail recursive. So they'll never blown up the stack, as normally like function composition could in Scala.
Right. Yeah. Okay. That's the relation I was thinking in my head about that.
Yeah.
Okay.
So there's a very good paper which was written by Runar. And I don't remember the name. I can Google it in a minute if you're interested. So basically, he explains what free is, but he starts with tail recursion. What it is, what are the challenges on the JVM in Scala? Then he implements a trampoline, and then he generalizes over trampoline to give you free. So it starts with tail recursion, and you end up with free. And there are like intermediate steps. So there's a really cool paper. It's not one of those papers that you read and you're sort of like which way I should actually read it, which is right. It's more like you can actually enjoy it while having beer. So I can Google it for you if you're interested in it.
That'd be nice.
Thanks,
Cool.
Max.
Well, thank you.
All right. Desktop.
I'm
stop.
never gonna go to sleep
Oh,
if you don't
stop
stop
yours.
sharing.
Stop mine.
Yeah.
You don't want to parallel?
Is that a bug?
Close it?
No.
Or is it a
I'm
feature?
not sure if it's a bug or a feature, actually. I know why it takes me.
I'm not sharing. Right?
Yeah, I don't think so.
Okay, cool.
Yes.
feature until unwanted behaviors.
All right, so I have two presentations here, and I'm not going to show you both of them because that will take like 2 hours. But I'm thinking, since we have this little small group, we could sort of like decide of which topic is more interesting. So I have like a few questions to understand like what kind of audience I'm dealing with. So how many of you guys actually like do things in Scala? Like Scala is your primary language? One person, two people. Okay, how many of you guys actually seen Scala in your life? Okay, majority. We could do, okay, so how many of you guys actually like understand the very basics of FP? So let's say type classes. Almost everyone? Okay, functor, applicative. Okay, so majority of people. All right, so I have a general idea what we could do. I would basically show you what my sort of like opinions about the power of writing code which is abstract. How about that? And we will cover things like what's the power behind abstraction, and also MTL, which sounds like it's a acronym for Monad Transformers Library, but it has very little to do with Monad Transformers really. It's sort of like a better thing to deal with composing effects better than the Monad Transformers. Does that sound sort of okay? Awesome. So, yeah, we're at the end. I'll be just covering a few things from this presentation. As I said, not everything, only the important part. So, there we go. Okay, so not this way. Wait. Panda. Yeah, we're almost in the middle of this presentation. So, you guys see a method here. Could anybody tell me what this method is doing? Like if you have problems, there's comment. Anyone?
It adds two integers together.
Yes, that's what I thought, but then apparently it doesn't. So as it turns out, your name of your function is actually also a comment. Luckily, our industry grew to this level to understand that comments aren't necessarily telling you the truth. But I also have a statement here that the name of the method will also not tell you the truth behind its implementation, and might be deceiving, and it's not really a cool thing to have. I mean, only to reason about your software. Now, if you come from imperative world, and you see a method, you see some arguments, you're sort of doomed to look at the implementation because you never really know what's going on internally, right? It might be returning you that integer, but it might be calling database, might be launching nuclear weapons, might be doing anything at this point. So, but I have a question. What would happen if we would, let's say we want to stay in the FP paradigm, we'll not be doing any imperative or any not FP code base, and we will have just pure function. If we had a definition like that, so we completely abstracted ourselves, so it's no longer we are summing two integers together, but we are dealing with some a's, a1 and a2. What is the possible solution that we could have here if we are in the space of if we're doing only FP at this point?
Return A1 or A2?
We can return A1 or A2, and that's basically all we can do, because we don't have this ability to construct new A, because we have no idea what A is. In a previous function, here we could do pretty much anything, right? We could return I1, I2, we could return 0, we could do some multiplications, the space of possible solutions is infinite. But here, we can either return A1 or A2, and that's it. So we made our function a little bit too much abstract, because we still would like to sum those two things together, but now our function is too much abstract. We don't really know what A is. We cannot really do anything about it. Luckily, there is a type class, and we'll be using code which is from Scala Z, one of the Scala libraries that allows you to do FP in Scala. And there's a type class called semigroup. So what a type class will give you is basically saying if you have an instance of this type class with a fancy name semigroup for F, then if you have two Fs together, like F1 and F2, I can give you an F back. And there are some laws behind semigroups. So there's like what's the name of it? I forgot. If you have like you're summing A plus B plus C, the order doesn't really matter of how you associativity exactly. But at this point, like if we now constrain our A to be semigroup, which I forgot to do in those slides because here I'm supposed to put that constraint on that A. So in real life, if those slides were correct, this would look something like there would be like some working on some A, but it would be any A. I would say it needs to have an instance of semigroup, and then I have A1A, A2 of type A, and now I could use that plus operator from semigroup, so I could just say A1 plus A2. So I'm just saying I'm missing here in slide. There's basically an error here, but if you can just imagine that's basically here, right? So now you loosen our constraint a bit. So it's not any A. Previously, it used to be any A. Now we are saying it's an A. So maybe it's better if I actually show you. We're working on for a moment on something that actually makes sense. So this. So before that, if I had just that, right? I could just simply tell you A1, A2, and that's it, and it's not enough. I need to loosen my constraints. So now I'm saying it's not any A. It needs to have an instance of the typeless semigroup, and if it does, then I can sum those two things together. So now, not only our implementation here became more general because we no longer have to deal with integers. We can deal with anything as long as we provide the instance of that of semigroup for it. But also the possible space of possible solutions is like super small. It's either A1, A2, or we sum those two things together, and that's it. Now let's look at some other examples. So let's say we have another function like sum. This time we take a list of integers and we turn an integer back. And here is the proper implementation. It's basically fold. We're starting with value 0 and we sum all those integers together. Like, hopefully this makes sense, right? Yeah. So now it's a proper implementation, but one more time, the overall space of possible solutions is infinite, right? I could give you an arbitrary integer like 0 or 3. I could give you a first element of the list, or maybe second element of the list, or maybe like do some calculations on those elements of that list. So the possible space of all possible solutions is huge. So now we could generalize it. We could be a little bit more abstract, and let's see what that gives us. So we could abstract over that integer one more time, right? We could say it's no longer a list of integers; it's a list of A's. Now, in order to actually do something, because it's no longer an integer, it's some A, we could one more time constrain ourselves on that semigroup. So we have that plus operator, but we don't have the 0 argument for fold. Luckily, there's a type class, it's called monoid, and monoid is nothing else than semigroup, but also with that one additional function called 0. It's like a 0 element. So if you have like two integers, your 0 might be 0, and your append operation will be plus. Or 0 might be 1, and your append operation will be multiply. Or you could have a string, and 0 will be an empty string, and append will be concatenations of those two strings. So now, once you have that, you can implement that list, that fold, and you take that 0 from that instance of your A. So you're constraining your A. You can run this function with any A as long as you have an instance for monoid for that A, which is already pretty cool. But there's still the number of possible solutions is infinite. And now there's a question: could we go a little bit more further? Like, could we abstract a little bit more? And if you look at this function really closely, you will see that okay, we are using a list, right? But there's not that many methods that we are using from that list. What actually we're using from the list API? Fold. That's it. Our definition of our function, the signature, is taking a lot of power, and that there's a lot of power in that signature because list is a very complex type. it has all those different methods that you can use. You can have tail, you can have head, you can do all the crazy stuff with lists, but we are only using one thing, and that is fold. Luckily, there's a type class. So it would be cool if we just say, instead of having a list, let's have some f that holds a. But at any, I mean, if that will be any f like that, we wouldn't have possibility to implement sum at this point. Well, we could just return 0 for monoid, but that's not where we're hoping for it to get. So there's a type, yet another type class. It's called foldable, and now foldable has one method which is called foldMap, and based on that method foldMap, so foldMap takes your FFA, has a function that goes from A to B and will give you B from that f. And based on that method, there are a number of different methods which are implemented, and one of those methods is a method called fold. And if you look closely at that signature, it's basically what we pretty much need. So it's telling you this: listen, if you need to have an instance of foldable for your f, so you need to have this, right? If you have that instance, then if you have f of some m, and there's a monoid for that m, then I will give you m back. I will fold everything for you. And the implementation is using that fold map underneath, which is exactly what we have. Because we're saying we're gonna get some a's, which will be closed over some f. We have absolutely no idea what that f is. We don't know. It could be a list, it could be an option. We don't know at this point where we're implementing this function, we don't really care what that is. But we know one thing, that f, and one more time there is a back here that's supposed to also be foldable at this point, that f has an instance of foldable. So the implementation looks like this. And that's it. That this is all we need to do at this point, because all the magic is done one more time here. If you have some values closed over f, that f might be your list, right? But at this point we don't care what that is. And those values, they have an instance of monoid, and I will do all the magic for you here. And this is really cool because at this point the implementation is really, really short. The number of possible spaces for your solutions are very, very narrow, because there are basically two implementations that will compile for the signature. You will either return 0 for monoid. This will compile. This is not what we want, but it will compile. Or you can fold. That's it. Nothing else. And one more time, this function is more general in the sense of how you use it. Previously, we could only use it as a list of integers, and now we can have lists of integers as well, but we can have list of users, or maybe trees of something. It doesn't really matter what the signature, what the structure that we're using, or the values that we're having, as long as they fulfill those two constraints, so monoid for A and foldable for F, and one more time, the slide has an error because there's supposed to be a foldable here. As long as we have, as those two types follow those constraints, we can use this function. Possibility that we will have an error is limited. Now, Panda. The power behind abstraction is that you can solve problems in more general space and reuse them multiple times. So you might not be familiar with task. Task is like a future. It's like a future plus, future with some capabilities. So if you've ever been working on Scala in any project, at some point you will end up like with akka streams or whatever, you will end up in a situation that you will have a future of, let's say, int. In this example, task of int. But what you really want to have is just that task of int. You want to flatten those two tasks to get just one thing, just easier to reason about it. Now, I've seen, if you Google that question on Stack Overflow, the number of beautiful answers is like, mind-blowing. But the real answer is this: join. Now you might be thinking, okay, join is probably implemented something on task, but it really isn't. Join is implemented on this type class called bind. So in this example, you see I have an option of int, and I want to just have an option of int. I can call on that option of join, and it will flatten those two together to give me the final option of it that I want. Now, I'm not showing you this, but there is a type class called bind, And one of the functions that you will get on bind is exactly that join. So it's saying, listen, if you have an f of a, well, they're missing this here. This should be like this. But you can actually have, you see this in the comment, right? If you have an f of a, I will give you f a back, as long as that f has an instance for bind. Another example would be, what if I have a list of tasks of integers, but what I really want to get is a single task that will give me a list of integers. So let's say I have from different sources, I'm fetching the data. I'm fetching data from that database, and also I'm fetching data from, I don't know, whatever service. And that gives me a list of those tasks or futures or whatever. What I really want to have is a single task that will give me the list of those values. And one more time, I've seen this at least twice being re-implemented in the projects I've been working on. But the solution is one more time just calling the sequence on the problem. And one more time, sequence is not something that is implemented on list or on task. There's a type class called traverse. A traverse has a very neat method called sequence. So it's basically saying, if you have something like f of g of a, I will give you g of f a back. So it's just like turning this upside down, as long as f has an instance for traverse and g is applicative. Where applicative is yet another type class. So the lesson from this example is basically that we could provide a solution for very general types. Once we abstract, there's probably like a single implementation for this. For this signature, it's really hard to implement something else that will compile and will do what we actually want it to be doing. And also, we can use it with whatever types that we want, as long as they follow the constraints that were given by those implementations. Does it make any sense for you guys? Because what I got from people, so the next presentation is about MTL, and when I gave a presentation at one Scala conference, the people were saying that this is basically stupid, it's like too much abstraction, and what's the point? And for me, abstraction, there's like a lot of power I can get from abstraction. Once my code is abstract, not only the probability of having a mistake is becoming very, very low, but also it becomes more general, and I could use it in places I never imagined I would use it. And there's this sort of like lesson about this from this part of this presentation, and there's a panda for you. Okay, so now MTL. Everybody's ready? Prepared? MTL. Okay, I did this on the conference with this, because there's gonna be a lot of code, so please stay with me, and if it's already too much, let me know. We can have a break, or we can go to bar, and, whatever works for you. But just stay with me, because the amount of code is just horrible. And as I said, I'm using Scala Z, but if everybody's using cats or whatever, they should be fine. So MTL stands for Monad Transformers Library. And as I said, it has it has a little bit to do with monad transformers, but not that much as you think it does. Back in the prehistoric day of Haskell, when they came up with this idea of monad transformers, they had both monad transformers and type classes, we will see in a second, in one library. After a while, monad transformers evolved and they went to the main language, while those little type classes stayed in that library. So now when I'm saying MTL, I will be talking about those type classes which you can find in Haskell, and they were ported to Scala Z as well, so we can use them in Scala. But the general idea is pretty much the same, regardless of the language that you use. Have any of you guys seen this game? You haven't? It's so awesome. You should play it. It's like, you can Google it. Just Google Unicorn Startup Simulator. Basically, the idea behind the game is that you are the owner of your own startup, and the game will throw events at you. Like different events will happen, and you have to react. And depending on I couldn't resist. Sorry. And depending on what decision you will make, your company will thrive, but it will just disappear from the market. Now we're gonna do exactly that, the same thing. We're gonna run our own startup. The difference between our startup is that we sort of are dealing in a galaxy far, far away. So we just founded our startup, right? And luckily, we have our first client. Not only do we have our first client, it's also the client's actually government. So it's pretty cool because they have money, Great. So what's the problem that the government has? So they used to have a very cool application, a very monolith application. And then one of their developers went to this conference and had about this thing called microservices, and he said, like, we should decompose our thing to microservices, and this thing happened. So now they don't have that much money, and they need to go from citizen to citizen and collect money using taxes. And they need an app for that, and this is basically what we're going to implement. So after having some discussions with the client, our business analytics said that basically that this is what we need to implement, income tax, and the logic behind it is that whatever the given citizen earns, we subtract 5 from it, and 5 is for the citizen to sort of sustain his life, and the rest is our income, it's our tax. So the logic is very, very complex, I know. Luckily, we are a startup, but the first thing that every startup does is acquire another startup. So this is what we did. We acquired a different startup, which has this little neat library, which is exactly what we need, right? It's just taking an integer, and it gives us the integer with subtracting -5. It's basically what we need. So, all right, having this function in this third-party library, let's try to implement our income tax function. So we just call it -5 with our integer, right? Should be good. We have this main method here. We take the income from the argument list, and we call our income tax function, and let's see what happens. So we will call our main method with 2 arguments, 10 and 4. And right, for 10 we get the right result, income tax equals 5. However, for 4 there's some exception, and we realize that our third party, they actually throw exceptions if the value is smaller than 5. So we would like to stay sort of in like pure FP while we're running our startup. So we have to sort of deal with the problem of what happens if we have an error. So we came up with the solution that, all right, our signature of our method will change. We will not return you an integer back, we will return you a try of integer. So try, basically what it's doing is internally calling your method. If there's an exception underneath, it will return you a failure. If there was no exception, it will give you a success. And having that new signature, we can call our function with income, with those 2 arguments one more time, 10 and 4, and it gives us a proper result. So for 10 we get an income tax back. For 4 we get actually an error that the value has to be greater or equal to 5. Now, closing that integer of a try is not the only way how we could deal with errors. So the other way we could deal with it would be just closing this over a task. So in our income tax, instead of returning a try, could return a task of integer. So here we are calling this function. So we get task of integer back. We are mapping it over, so we get an integer. Then we have this handle with method. It's implemented within task. So what it's saying is that, well, listen, if there was an exception, like some kind of error, just return the message of that error. And then at the very end, like in task, at the very end, you have to just call a method that will sort of evaluate your calculation. So the difference, main difference between task and future is that if your function returns a future, the calculations are already running. Like your method gives you a future back, the calculations are already running, while in task, it's still just a recipe of what should be done. Nothing is executing itself until you actually call unsafe perform sync. So this is yet another way of how we could deal with that error. Is task has its internal ability to deal with errors and handle those errors with methods like handle with. And that's not the only way how we could implement it. We could just pretty much ignore the error. We could say our income tax it returns an option of integer, right? So we could just say if the value is correct, we'll give you integer back. If it's not correct, it will give you none. And if we run it, we get the right result. And with the wrong argument, the call is basically pretty much ignored. Now somebody might say that, well, this is not really the way how you actually should deal with errors. The better way to deal with errors is with either type. And either type in Scala Z has this weird operator. You might look at it, you might be really confused. What the hell is that? Think of it like we should here, for example, we have a throwable or int. So it's like so you might ask income tax, where are you turning? And income tax will be like, throwable or int, I don't know. So this is like how you should think about it. So and many people will say like this is the right way to deal with errors. So you should return an either type. And we call this method with our argument. So we either get right hand side, right 5, or the left hand side, the exception that was thrown. And now we are sort of like there is a problem, right? Because we are defining our function that will be used by somebody else, but we have to make a decision up front. We have no idea how the function is going to be used, right? Some might be calling this and need actually an either type. Somebody else is actually dealing with like values from database, so they would rather have a task here. But we are making this decision up front without even really knowing how this function is going to be used. It wouldn't be just better if you had something like this? This is like, given what we learned so far about the power of abstraction, couldn't just have our function income tax be abstract? We will give you an integer, and you will get an integer back. You will get that tax value back, but it will be closed over some f. Now, what f? We don't know. You tell us. You have the power of telling us what should be the final type of the thing that is being returned here. Now, how we could implement this function? Well, if we go to Scala Z, there's a type class called applicative. So applicative has this very neat function called point. It's basically saying if you have some a, I will close that a over f. So let's say you have an integer 10, and there's a type class for, let's say, option. You could call 10 point option, and it will just close that value 10 over that option, or whatever f that you have. So having that in mind, we could say our income tax is constrained by applicative. So now, if we have a success, we could just call the value of that success point f, and that will give us that f back, right? So we have, this is covered. Like, does it make sense? Any questions? Or this is like super weird? Who's lost? Who's already checking Twitter? So far, so good. Like, we have a success scenario. We have a value, which is an integer. We need to lift that integer to f, but that's not really a problem because applicative pretty much covers that functionality, has this ability to lift this into our final f that we need. But the problem is, what should I do with a failure? This can fail, but and we are closing over some f that should deal with failure, but we don't know what that f is. It could be a task, it could be an option, could be an either type, could be try, we don't know. So what can we do about it? You should see a pattern here, and we'll be constantly repeating there's a type class for that. So there's a type class for that called monad error. And monad error looks like this. It's constrained by two things, that your f, and in our example this is exactly the same f, and some s, where s is the error type. And it has two methods, and actually we will just cover it as one single method, rise and error. So that method is basically giving us what we really need. We have some error, and we would like to close it over our f. Now, if this seems confusing, you might be thinking like, how does it happen? Like, what are the internals? You don't really have to care. That's the beauty about functional programming, that whatever is complicated, you just postpone it, like somebody else maybe will deal with that. Here, we don't really care how that raise error is implemented. Somebody will call our function income tax with some f, and they need to provide an instance for applicative, and they also need to provide an instance for monad error. So we are saying here right now, not that f cannot be really any f. It has to be an f that has an instance for monad error, where the error will be throwable. And now, when we have that failure scenario, we can take our e, where our e was that throwable, and lift it to f using that function. One more time, just to show you the signature. Our s here is a throwable, our f is our f, whatever that is. We still don't know what that is, but as long as somebody gives us an instance of this thing, there will be implementation of this function. So whenever we will give them a throwable, they will have ability to close that for loopable over that f. And this is what we're doing here. Now you might be thinking, okay, but you just erased applicative. What the hell is applicative? Well, if you look closely, you will see that monad error is still a monad, and monad is applicative. So you still have that point function in it.
So, Paweł,
Yeah.
So why isn't there is there an applicative error? Why did we have to jump to monad?
That's a very good question, and we will cover that. That's a very stupid design decision, and there is a lot of pain with that, and they will be covering this in the latest version of Scala Z 8. Scala Z 8 is complete rewrite of internals. They are rewriting everything. So they are having all they learned from the mistakes that they did. They're just doing the complete rewrite of the library. And that's a very good question. Not only why does it applicative, why does it have to be anything, right? Yeah, and we will see at the very end of those slides why this actually it's very, very painful.
Quick question.
Yeah.
So one thing that's been different from previous slides of this one has just been the introduction of that implicit. Like, what's that for? I'm not terribly familiar with that.
How to explain that? Okay.
Registry.
Like, what's the difference between the previous slide and this one?
There's a synthetic sugar, basically. I actually had some. Let me quickly show you that. Can actually recreate my code, yes I can. So really quickly, let's say you have a user, right? And you have a function like this one here that will, given the user, you want to say like hi and the name of the user, right? And now, so this is basically like recreating type classes, but I will show you like how that works. Or maybe should I just? Well, I'm thinking about this. Okay, so give me a moment how to explain this. That implicit here gives you an instance of that type class, and in Scala type classes they don't have the type classes are not first class citizens. They are not built within the language. There's no such machinery like in Haskell where type class is just a thing within the language. What we have within the language is something called implicit. So it's basically you have this ability.
That makes sense.
It makes sense.
Like constraining the message you can call that thing to only be
those two signatures. Let me delete all that. Bye. So those two signatures here, this one and that one, will be equivalent. Give me a second. Show. Those are equivalent.
Okay, yeah.
This is like a synthetic sugar. The only difference is that with this guy over here, right? I could just use that type class. So I could just say show A, right? While here I'm just saying A has a type class of show, and well, how can I use it? I would still have to say like something like show A. That would give me an instance, and then I have to call show. But those are like, if it's confusing, just bear with me. Those two are equivalent on the bytecode being generated. This is like a synthetic sugar. This is synthetic sugar from the thing from the line 21.
Okay, yeah, that makes more sense.
Sorry.
No.
But does it make sense at this point so far? Like, does anyone has any questions about it? This gives us this nice little feature that user who will be calling our method has the ability to choose which type is going to be returned, an option or task. We don't really care, and all the craziness is being pushed also back to the user. So we, as the method implementators, we are not really doing anything at this point, right? Because all the things like raising an error is pushed to the instance of the type class. All what it means to lift a value to that f is also pushed to that type class. So we just called two functions which were given to us, and we're not really doing anything at this point. The implementation of this method is pretty dumb, but we get all the power. Basically, what we covered so far, like the power from the abstraction. Now, just to see how it works, but I hopefully you guys see already. Like, given that I have I'm introducing here an error type, which is which is this junction. This is either throwable or some A. I could call my income tax and just parameterize this by that error, and it will work. I could parameterize this by task, and it will also work. So if I call those functions, if I'll just call this main method here, and I will call income tax with both with income and both with error and task, what I will get is, for the positive scenario, I will have either back or task back, or I will get left side of either back. Whoa. Wow. That's so cool. And that task here, so I will just point here, and task as well. So depending of what I've provided here as that F will give me a different result back. Now, what about an option and try? Well, there are no instances of monad error for option and try. So could we still call this function with option and try? What we should do to call those functions with option and try? We would have to implement that instance. So let's do just that. So as I said, monad error is a monad. So we have to provide all the functionalities for monad. So we have to provide point and bind. So it doesn't really matter at this point. Just believe me, it works. It compiles. So let's just focus only on this rise error method here. So what does it mean in terms of an option that there was an error throwable and we need to return an option back? Because remember, in terms of option, we were sort of ignoring that error, right? So the only implementation that makes sense here is just returning none. And it works. What about try? Try is pretty much exactly the same. So if I have an error throwable and I need to return try, I'm just returning that failure case, where failure takes a throwable as an argument. And that's it. And now I can call my income tax method here with disjunction, with task, with option, with try. Those two first guys, there still need to be an instance for a monad error for those, but the instance for those two exists at Scala Z. And it's imported by default, so I didn't have to write anything. For option and try, those didn't exist. That's why we have to provide them, but we provide this once. This little monster here, because I also believe it's ugly, but it's one in one single place in your code base. You provide it once. It's in this little implicit keyword, gives you this ability that it lives in implicit scope, so it's available everywhere. You create it once and you can reuse it. And now this will work for whatever type that the user gives us, which is pretty good. Cool. And if you think about it, you give the power back to the user. But not only that, you give the power back to the user, there's also one little cool feature that you also get for free. And that is, let's go back to that previous implementation, the naive one, the one without monad error instance. So this is not what you normally see. Income tax should give you an integer back, but there might be an error, so there's a disjunction, so either throwable or int. And this is what we had before. Now, let's say there is another function called environment variable. So for a given name, it will give you a value of environment variable within the system. Now, because that's a side-effecting function, it's calling your file system, it's closed over task, right? We still want to be purely functional. So if something is doing something which is sort of changing the world, we close that over task. As you remember, task will not evaluate itself immediately. You're creating like a recipe of what should happen eventually once you call it. So we have two functions with two different signatures, and we would like to have a function, finally our main method, we would like to have from the arguments list, this time we don't want to have a value back, we want to have a name that will represent some environment variable which holds the income. So we will first call our environment variable with our name. This will give us that value, and then with that income, we would like to call our income tax method. Now there is a problem because that for comprehension here, which is like a do notation in Haskell, like this is one of those things people say in FP community, right? That monads do not compose. We cannot really call those two together. Those are different types, and they don't compose. Disjunction, either type, does not compose with task. So one of way of doing this, like dealing with this situation, is using monad transformers. So there's an either T. So either T, there's nothing really special about either T. Either T just wraps over this little thing. Like if I have some F, like for example task of this junction, you can just wrap it up over that either T. I don't really want to focus that much on monad transformers. So if that seems weird, it should, and just stay with me. So now I can lift both of those calls to a single type, to either T of task. So now our final value will give that either T of task of throwable of int. And we can lift our task to that either T of task. We can lift our either type to that either T of task. And once they are lifted to the same type, now they can compose. And now we can use them in for comprehension. And the final value that we're going to have here is going to be of a type of either T task of throwable of int. So just a reminder that either T of task is nothing else as just say having a task of that disjunction here. It's just close over, wrapped within that class. So if you sort of are in ease and you don't really care about it, you seem fine, then check what happens if, let's say, our environment variable not only gives us a task of string, but what should happen if that environment variable doesn't exist, right? We call this function environment variable with a name, but there is none in the operating system. At this point, we should return a task of the option of string. And now the madness begins, right? If you are, like myself, ex-Java developer, you're sort of accustomed to boilerplate. Like you can sort of like train your brain to sort of see through the ugliness and reach to the very bottom of the things that are important. But I would argue like in this implementation, only those two things that are highlighted are really, really necessary and really, really what matters. Everything else is just lifting to the right type, so everything composed together. And that is just awful. Now, how this functionality would look like if we use monad error. We could say income tax is a monad error. And that environment variable, let's say it's still using the task and option of string. At the end of the day, we'll still have some option T of task. We'll still have this type over here, but all that heavy lifting will be done in one single place. We can call our income tax with the type that we really need at this point. And at this point, we need option T of task. And it will know what to do with itself. Like we don't really have to care about it. The boilerplate still exists. Like you might wonder, okay, so is there a monad error instance for this weird thing like option T of task? Well, there is. And if you look into Scala's sources, it's saying like there is monad error for option T of F as long as there is an instance for monad error for that F. So it's like, is that for any option T of F? As F needs to be also constrained. But we have it. And by the fact that we don't really, in the terms of implementation, we don't really care what that F is, it can be used in different scenarios with different types. And we don't really have to suffer. And it works, and you can believe me that it works. Now, our client is happy. Let's go to another client. Our legal department is telling us there is no conflict of interest, so let's just work with Princess Leia. So, like, who's already like suffering? His brain is already like damaged. I mean, are you still fine with going through this rest of this presentation, or is it already too late for your brain? Like, we're good? Hopefully. All right. So, if you have enough, just let me know. So Princess Leia have this like. There's a problem with running a rebellion. Like everything is fine, but those rebels they just keep on dying constantly, and it's like really hard to run a rebellion when ships are being destroyed and rebels are dying. It's really hard to fight an empire. So she's like saying, I need to keep a track of my spaceships and have some reports of how things are doing. So this is a little bit of the main here. We have a gun, different types of gun with different power. There's a drive, which requires like a minimum a number of personnel, and there's some tanks, so you have to put fuel into it. And there are different types of drives. And there's a concept of a citizen. And at the very end, you have a spaceship. So spaceship has a name, has a captain, who's a citizen, has a drive. There's a list of personnel other than captain, and the fuel, and the front gun, and the rear gun, right? Nothing really fancy about it. Now, there is a method called init that allows you to construct a new spaceship. So you provide a name, you provide a captain, and you provide a drive, and it will just call that constructor for you. So the number of personnel will be, the list of personnel will be empty, the fuel will be 0, and there will be like front gun and rear gun will be by default equal to laser. Now, since we are staying in pure FP, and Princess Leia needs functionality to sort of assemble a spaceship that will be ready to battle, in pure FP, if we are changing the state, there isn't really much we can do. We have to take the initial state as an argument, and as a result, give you a new state back. And so that's what we will be doing here. So there's, for example, a method called recruit. You give a spaceship, you give a citizen, and what you get back is a new spaceship, where in that new spaceship we add this citizen to the list of personnel, and we also return a Boolean value. We are returning a Boolean value which represents whether the spaceship is operational. Meaning, like in this example, the answer is whether the number of personnel is equal or greater than the minimum number of personnel needed to sort of deal with that drive that we have in our spaceship. And there will be equivalent method to sack a citizen from that spaceship. There will be ability to put fuel into our tank and equip a front gun and rear gun. And it's the signature is pretty much the same. We get a spaceship at a given state. We give you a new spaceship back, and also we'll give you some additional information. Like for example, when we equip a weapon, we also give you what's the overall power of the spaceship at the given moment. Now, this looks, well, pretty okay. Now, if we try to create a test for it, so in this example, we have two citizens, Han Solo and Chewie, and we create a Millennium Falcon with Han Solo as its captain, and that gives us a spaceship back. And then we recruit Chewie, which gives us an answer whether a spaceship is operational at this point, and new spaceship back. And then we put some fuel into it, and then we equip it with some weapon for front gun, and then we change our mind, and then we put a rear gun at the very end, and we run status report. It already looks ugly, but that's not the only problem. There is a bug here in this implementation, and we'll see that bug when we run it. So we run this functionality, and then we get our report back, which says that we have this spaceship, Millennium Falcon, captain is Han Solo, there is a Chewbacca here as one of the people on the personnel, but we see the antimatter blaster and lasers as a gun. But if we look at our code, we put antimatter blaster on both front gun and rear gun. What happened was that last call gave us this last little strip S6, and we printed out this with S5. It's really easy to make an error here, right? An error that we have to pass that state around, but the problem is, like if I make an error, compiler will not complain. And what I'd like to have from the language that I use, strongly statically typed language, is that I'm just a human, humans are stupid, so if there's an error, compiler, computer should tell me. So can we do something about it? Luckily, there is this thing called state monad. Now, if you go to, as I said one more time, there's a typecast for that, right? But if you go to Scala Z sources, and this is what I did the first time I heard about state monad, I went to Scala Z sources, I looked up for state, and in front of my eyes I saw this. For me, it looked like that, like, what? Like, there's even like, what? So in order to try and understand what that is, we could do something else. We could recreate state monad from the scratch. Now the question is, how many of you guys are not familiar with state monad? Okay, few people. Great. So let's do that. So state monad. So this will be like a very naive but working and production-ready implementation of state monad. There's no magic behind state monad. What state monad is doing, it's basically a class that wraps a function, wraps that function internally, and a very specific function, a function that goes from some s to a tuple s of a. You can already see the resemblance of what we are having, a spaceship to a new spaceship and some value, like for example, whether this is operational, yes or no. There's no magic behind it whatsoever right now. It's just wrapping that function, and that's it. Now the question might be, why is it doing this wrapping? That's a different question, but in terms of what state is, that's basically the definition. Now, being so here we have some sort of like a factory method. So given a function from s to sa, we will construct this object with new state, and we're wrapping this function here f. So now, as being a monad, you have to, at least in Scala, implement those two functions, map and flat map. And what I find really, really cool about functional programming in general is that even though I have absolutely no idea what I'm doing, I can still be correct. And yes, that's like it's better than Stack Overflow, really, because like you can be pretty dumb and still be doing the correct stuff. So here, the question is, can we implement map and flat map for state? And some of you guys, especially for those of you guys who don't know what state is yet, or just trying to grasp the general concept of what it is, you might be thinking, what? Like, this is just too hard. You just started explaining what state is, and you want us to implement map and flat map. Cool thing about functional programming is that a lot of times there's only one single implementation that will compile, and to get that implementation, all you have to do is follow types. So let's try to do that, just that. Let's try to implement a map function just by following types. So we need a function that will return state as b. What state as b? Can you remember what this thing will be wrapping? State as b. What this will be wrapping a function, right? What kind of function? From s to s and a, s and b, right? This is state of sb. So it's this thing that will be returned here. Whatever we will be returning here, it will be wrapping a function that will go from s to a tuple sb. So let's just do that. So we just created that object. Now this object has to wrap this function. So those question marks, we should put this function, right? So as we said, it will be a function that will go from s to a tuple s and b, right? So how can we get b from?
Call G.
Was that?
Call G.
Yeah, the only way we could get b from is by calling g. We call g with an a. Where can we get a from?
Call F.
Yes, if we call f, right, we will get a tuple, a new s, and that a. F needs to be called with an s, right? Where can we get s from?
Line above, S0.
That's S0. And at the very end, we had to provide that b and new s. Where is that new s? S1. And that's it. And that's the only implementation that will compile. That's the only implementation that works. You just follow types. It's seriously better than Stack Overflow.
Just don't return S0.
Was that?
Don't return S0.
Oh, well, yes. Damn it. Flat map is pretty much the same. I don't want to bore you with details, but if you follow the types, you will have the same implementation. It's just a little bit different, but it sort of works. So now, having this, we have this function that takes a spaceship and gives us a new spaceship and some value boolean, right? So there's an easy step to switch that to instead of returning a function, just to returning a state. What should I do with all those methods? I can just wrap it over state, right? State, as you remember, state wraps over a function. So if I have here a function that takes a spaceship and gives me a new spaceship back and some value, this is exactly what we're having. Spaceship, a new spaceship, and some value like Boolean or whatever. So I could just wrap this function over a state. There's like, you might see it, not really a lot happening. I'm just taking this function and wrapping it over a state. That's all what I'm doing. So the difference isn't really huge. We have functions and we wrap it over a state. So it might be saying, what for, right? And I agree, what for? If anything, it just looks a little bit more complex than what we had a moment ago. Instead of having function, now the function is wrapped over this object. What the hell? Well, the benefit is when we use it. So now, this is what we had before, and as you guys remember, we were passing that state around. So we were, between the function calls, we had to push the state from one function to another, and we could pretty much make an easy error. This is how it looks like if those functions return state. So now we write this for comprehension, where on the left-hand side, we only get that value that is being returned within that function. So the function was giving us, it was taking a state, and it was giving us a tuple S and A. So what we have here on the left-hand side is that A. So here in this term, in this example, that's Boolean, where this is optional. Here was the level of fuel within the tank and all that. State is being passed around between function calls. If you haven't seen in your life for comprehension, it's basically underneath we're using those map and flat methods which we are just implemented. But the only difference is here that this recipe is the type of this thing is still state. It's a state that takes some initial spaceship, and at the very end will give us this tuple with a Boolean, whether this is operational, amount of fuel, and the overall gun power from our guns. So in order to actually get those values, we still need to run our final recipe with some initial state. So in this example, in the place where we're implementing this, if I, instead of calling this an F, if I could call it just, sorry,
Just tap in.
okay. If I just call it, that instead of calling this an F, I could call it run, right? I could get access back to that function, right? That function I could wrap over a state, I could get an access back. So here, here I'm building this recipe of how to assemble my spaceship. And so at the very end, that recipe is still a function. Underneath, the type of recipe is state. State of spaceship and this tuple here that is being returned. So if I want to get those values back, I need to run this function, I need to execute it. I have ability of doing that by calling run. So run gives me this ability to call this function that is being wrapped underneath. And I'm calling this with initial Millennium Falcon, Han Solo, and some initial drive. And we get those results back, and we are sort of happy. So that's so far so good. Like, one important thing is that it's really hard for people who are sort of like mind blown at this point and might be like, your brain is already like in a lot of pain. You might be thinking, there's a lot of effort here done in order to create something I could have in object-oriented programming done for free. Somebody even laughed like, oh my God, this is how you create builder pattern in Scala. And like, no, it's not. I have to keep my example somewhat simple to explain the stuff I would like to explain in this presentation, which is MTL. However, that in order to explain MTL, I have to build those foundations for you as well. So I know there's a lot of stuff to cover, but just take, like, believe me, it kind of makes sense at the very end when you actually write functional, like pure functional programming software. So, any questions towards that? Like this, there isn't really much magic behind it. In order to stay purely functional, when we create that final ship, we would have like those little functions that there's a function to recruit a new citizen, there's a function to put fuel into tank. All those little functions do separate things to finally compose our final spaceship. when we had this naive implementation where we were passing this spaceship around that introduced a lot of problems, and we solved that problem with a state monad, because that state monad is pushing that state between the calls, between one function call and the other. Now, so this has nothing to do with MTL. It just sort of is an introduction to what a state monad is. Now, why I was covering that for this presentation, and the reason for that is, let's imagine that instead of having Chewy as an argument here, like Han Solo and Chewy were arguments that we're just running when we created a Millennium Falcon, and we were recruiting a Chewy to be one of the people who would be operating the spaceship. Let's say we get Chewy from this function called Wookie, where you provide a name and you get an either type. You get either a string with an error message, or you're a citizen. So instead of providing Chewy here as an argument, we would like to retrieve him from this function. But as you remember, monads do not compose, right? So those little functions, they return a state back. This function returns an either type. So it's not like I can call Wookie here by name. This will give me Wookie, and then I could call recruit. In order to do so, I would have to lift both of those types, so both either type and my state, to a single type, right? Using monad transformers. And this is how it looked like. Madness. Like, if you look at it and if you call it state of FB, at this point you just might close your computer and go home. Because it's just horrible. Like, try to reason about this code. It's just impossible. There's a lot of boilerplate. There's not a lot of going on in this function. It's still the same for comprehension that we had here. The only problem is all those calls have to be lifted to the same type, to the type that has ability to reason about error, and the type that has ability to reason about state. We need to have a type that will have ability to deal with both effects, both errors and state. And that type is either T of state of spaceship. But when you try to use that type, you produce something that horrible, and I guarantee this is not production ready. Now, to make things worse, Princess Leia said, like, not only we need to provide this status report of our spaceship, but if actually spaceship is operational, we should also include that status report internally within the spaceship. So whenever spaceship is ready for action, that status report should be included in that list. So not only this madness, but also there will be another method, status report. And that status report is just basically, like, you could try to reason about it for a second. You sort of see that if spaceship is operational, then I will create new status report and make it a new spaceship, and that will be closed over this state. And if it's not the case, then I have to make this error here, but it has to also return that previous spaceship. All the ugliness, and you might reason about it if you try really, really hard, but it's just awful. So, can we do something about it? Well, you might say, you might try to do a little like putting a lipstick on a pig, basically. So in like this whole big, huge, enormous type could be type aliased. So we could just say like ship state error, like exact. But yeah, it's not really doing anything about the boilerplate that we have over here. So, but still, we could do something like that. We just say like there's a ship state error, which is that either T of ship state, where ship state is a state of spaceship. It's just, when you see it for the first time, it's just horrible. Like, trying to understand just that is already an issue, and then you see something like this, it's horrible as well. If you just look at those type aliases, it actually makes sense. You're sort of stating here that whenever you will see this type, ship state T, it's a type that can deal with two different effects that might happen in your system. That can deal with errors and can also deal with changing state. But the problem is that ugliness here. So let's see if we can do something. Like, Well, maybe first of all, like one last thing to notice is the code that we produced over here. If we run it, it works. So now I have a question for you guys. Should we ship it? You're a software engineer, so you tell me.
I don't think Persistence Layer is going to look at the code, so it's fine.
Right? Yeah. Yeah. Well, there's this one single rule. You know, always code as the person who will maintain your code is a violent psychopath, right? You know how I got these scars. So I know we could ship this code and it would work, and Princess Leia wouldn't really care until she needs a new feature, right? And then you will give her a new invoice, and then she's terrified. So let's go back to this initial implementation that we had, the one that was using state. And I know I'm over time, so that it will be not more than 5 minutes. So please stay with me. So those functions were returning state. But one more time we make this decision up front. We needed a functionality that will have ability to sort of push that new spaceship between function calls. But we fixed on state at the very beginning, right? We said like it has to be state. The return type of those functions needs to be state. While the only thing that we needed would be saying, I should return some type that will know how to deal with the changing state, not necessarily this particular type class. So instead of having this, we could look for a type class from MTL called monad state. And monad state has this number of different methods. We will just focus on this one singular one called state. So it's saying it's basically the same thing. It's saying if you have a function that goes from S to SA, and there's an instance for monad state for your F, whatever that F will be, I will give you that FA back. So to just give you this, just give you a context of what we're looking at right now. That F can be our state. That F, there is an instance for state for monad state. So that F could be our state. But there's also one for state T. There's also one for either T as long as that internal thing has an instance for monad state. So we are saying we're giving the ability to wrap that function that goes from S to SA to whatever F. But you as a caller of our function, you decide what that F is. It can be a state, but can be state T, can be anything as long as there is an instance for it, for that monad state. So just to put you in a perspective in this example, previously we were wrapping those functions, like for example here from ship to a new ship and some Boolean value, and we were wrapping this over state. The only difference that we will be doing here right now is we are saying we will be not returning a state of spaceship. We'll be returning some F here. But we still wrap this function. We're still wrapping only this function, but now we are not dealing with a concrete type. We are saying any of F, and you as the caller of this function can decide. So we could just call this, in this example, this function with just ship state, where ship state is a normal state here, like we had before, because there isn't anything that we have to deal with. But if now Princess Leia comes with this new feature, include Wookiee, where Wookiee needs to have this monad error, it can be any F, we still need to have this final type that either T of ship state, like the final type that will have ability to reason about both errors and changing state. So we cannot really escape from this thing, but our call looks like that. The boilerplate is still here, but you guys don't see it because the boilerplate is hidden within the instances of both monad error and monad state for those little functions that we were using. At the end of the day, we still have to call it with a type that has ability to reason about those two different effects. but lifting those to the same type is done by your type classes. Now, I know it's pretty late, so I'll just skip that. This is one of those, I'll briefly cover this, that we had that status report, where status report had to give us an F, but it could be an error. So if the spaceship is operational, it's all good. We have to include the new report within our new spaceship. So we need to have this capability of changing state, right? But if it's not operational, we were supposed to give an error. So we need to have this ability to raise an error. Unfortunately, in Scala, this will not compile, and I will just quickly skip why that is. I will just quickly show you. But that's just Scala. That's not necessarily a thing in other languages. Unfortunately, both monad state and monad error extends a monad. So now, when Scala compiler tries to reason, like it will be like, well, wait a minute, like where should I get monad capabilities from? From this type class or that type class? So that's unfortunately a pain, and there are ways to sort of like overcome this, but I will not cover this. Just stay with me. It's doable, and also in Scala Z8, they're right now re-implementing stuff. So if you're actually doing FP in Scala, once they will release version 8 of Scala Z, dealing with monad transformers library will be a lot easier and a lot less painful. And the thing works now, and the princess Leia is happy. Now, what else? There are a bunch of other type classes in MTL. So, like monad reader is this abstraction over reader monad. Monad listen and monad tell sort of abstract different things from monad writer. So all those little things. So instead of using a very concrete type class, you can use a type class that holds that capabilities, but you're still not choosing which type class you'll be dealing with. Now, to sum it up, let me just give you a homework. Because if you really like this knowledge to sink in with your brain, try to write a function that will make a very simple exercise, like create 3 different functions. One function will return a value, let's say an integer, but within like an either type. So it might be an integer or error. Other function will return an integer, but let's say it will take a configuration as an argument. So you need like something like a monad reader or something like that. And the last one will let's say use state, or maybe it will log something with writer. First, implement that without MTL type classes that you've just seen in the last like 60 minutes or so. Live through the pain of actually so you have those 3 different functions, and now try to write a for comprehension that will, like each function returns an integer, and now write a function that will sum those 3 integers together. So integer 1 plus integer 2 plus integer 3. Obviously, you have to deal with error, configuration, and changing state or logging stuff. Now, the amount of boilerplate will be like this, and then re-implement the whole thing using MTL and see how that shrinks to just what you actually basically need. If you don't want this last 60 minutes to be wasted of your time, because if you guys are gonna go home and you'll think that this crazy guy from Poland, you think of your time as being wasted here. If you really want this knowledge to sink in your brain, do this little exercise, and I guarantee you will be happy about the final result. Now, for anybody who is just wondering what happened to our little startup, we were acquired and we were happy ever since. That's all I have for you guys today. If you have any